from UC Riverside, and she'll tell us about tensor graphical models for complex and high-dimensional data. Take it away.
Thank you very much for the kind introduction. So I first want to thank all the organizers and the tech support for making this event happen. So I first put a title called Gratitude on this picture because it shows, how it's all possible for us to still talk to each other at this difficult time. But then I found all the directions on the picture point to the north. So I guess I changed the title to directions. But I guess this is a way to say hi to my friends in Europe and hope, and also all the people in the studio hope someday we can talk to each other in person soon. So the motivation for this talk is from a gene expression data study, and the citation is given below by LePage et al. So in this study, they have some twin pairs. And so in their original study, they have both identical and non-identical twins, but we took the identical twins from the study. And these are called discordant twin pairs, means they one of the siblings has a particular disease called ulcerative colitis disease, and the other twin sibling is healthy. So the pairing of the data suggests that the correlation between sample exists a priori, and moreover, in many of the experiments, there may be unwanted or unexpected correlations from the sample, for example, due to treatment or due to some other environmental factors. And this is one of the important aspects in gene expression study, as pointed out by Professor Efron in large-scale inference, which he pioneered. So we want to use this example to motivate the high-dimensional and the complex data part of the talk. And so first, I want to just set up a mathematical model, which is sort of idealized, but can serve as a prototype to start the conversation about how to deal with the complex dependency arising from this type of data. So here I model the data, which is a microarray data, which is the sum of two components. One is the mean and one is the noise. So the noise has this complex structure such that it has both between sample correlation as well as the correlation among genes. So those are denoted by B and A. So B half denote the square root of the correlation among people, and the A half denote the correlation among genes. And then the mean matrix is deterministic. So here we just model using two-group mean, means the disease group has one high-dimensional mean vector, and then people from the control group share another common high-dimensional vector beta 2. So this is the model we start with. And let's take a look at this probability distribution of the errors. So here, epsilon, we model using this matrivariate formulation, which I elaborate below. So here we assume Z is some kind of random ensemble. So throughout this talk, I just assume Z is mean 0, variance 1, and has a Side2 norm being bounded. So the Side2 norm condition on a scalar just means the tail of this random variable is like a Gaussian tail. So we have a formal definition later. And if you just think of Z as ID, Gaussian random variable, that is enough to get you started with what's going on here in the model. So suppose we can transform the error by B negative half, and then we have this new error matrix, which is Z times A half. And this is something we feel more comfortable dealing with in statistics, because in statistics literature, we routinely say we have ID sample, and with ID means independent, identically distributed. So here, at least we make the error part independent, and with more definition on the Z vector, we can look at this Z a half as a random design which satisfies certain nice conditions to do statistical inference. So coming back to this Algorithmic collectors data. So here the reason we model the data such as on the previous slide is because we assume, as mentioned earlier, all the diseased sample share the same high dimensional mean vector, and all the healthy group people share another high dimensional mean vector. And then the genes are correlated because they, in the gene expression study, we know they are controlled by networks, pathways, and so on. So they are correlated in that sense. And then the noise will be correlated as well across all the samples, which is kind of an unfortunate, aspect of such a study, because we know if the noise is correlated, then you cannot really ignore those dependency. Otherwise, you will lose power in terms of statistical testing. So the starting point, of course, is we can estimate the sample mean, which is you take the sample average for the disease group, and then you take the sample average for the control group, and then you take this mean out. So you start from there, assuming the data is mean 0. So of course, if that's the story, we can just all go home today. And so today I'm going to present you a much more, complicated story, saying we need to estimate, the covariance B as well as decorrelate the data so that we can better control the inference part when we look at the gene expression data. So here is the high level technology is we say we treat each column vector in this gene expression data as a, in Rn, and we want to decorrelate. So we can model this, of course, by writing out the mean, which is a n-dimensional vector. And then we write out the noise as B half times Z, where Z is isotropic. And now if we can do B negative half in front of the centered data, so when I say centered data means I take the mean out from this high dimensional vector, and then Z becomes uncorrelated. So means the covariance of Z is identity matrix of in Rn, then we have a similar story as we commonly deal with. That is, we have isotropic, random vectors along each column for each gene, although along the, for each row, they are still correlated because of the gene correlation. So put in the matrix form, this means we transform the original data X into Y such that the deterministic part becomes B negative half times the mean matrix, and then the noise part is becomes independent for each column. And so this is a sum of a deterministic mean component plus a noise, which is isotropic along each gene direction. So we can design estimators to estimate the mean difference for each gene, as we already know in the classical theory, is to do generalize the least square. So means you look at the transformed matrix, which I put in the bottom. So the bold D represents this B negative half D, and then Y is the transformed data matrix as given here. And the beta hat, if I write in the transformed design and transform the response, that this is just the ordinary least square estimator. And if you put in all the bold D with the expression here, you get the expression for generalized least square estimate for each gene. Of course, so far, I only talk about how to estimate this beta hat coordinate by coordinate. Then later in the talk, I'll talk about how to do this jointly across the M genes, which is high dimensional object altogether, how do we select variables from beta hat? So the question is, of course, how do we estimate B? And so that comes to the next part of the estimator is, suppose we have a B hat and we will just do plugin. So we replace all the Oracle estimator where B appears with a B hat, which is the estimated correlation covariance matrix among the samples. And then we can, again, estimate coordinate-wise beta hat and calculate the mean difference for each gene, and then start to do testing from this gamma hat downstream. So for estimating, so I'll skip this slide for now. So for estimating B jointly with A, this comes to the tensor graphical model part of the title. So the tensor graphical model means typically when we do graphical model estimation, we assume we are given either independent rows or independent columns. But for the complex data, oftentimes you have dependency among both rows and columns. And if you have replicates, then you may have dependency across replicated matrices as well. So as I illustrated in the previous gene array microarray study, and so therefore we need to model the covariance and the inverse differently from the classical theory. So the first tool we have is to use multivariate modeling. So assume, as I said, assume the random ensemble Z as ID Gaussian, then we can write up this as a matrix normal distribution. So mean in the previous example is this rank 2 object, and then A Chronicle B would represent the covariance of the microarray data vectorized as a very long vector of size mn. And so here A would describe the correlation or partial correlations between and among columns, and the B would represent the correlations and the partial correlations between and among the rows, which are the samples. And the goal is to estimate A and B up to a certain scalar factor, because for a product of two things, you cannot estimate them up to, you can only estimate them up to a scalar factor. So the conceptual challenges, at least when I first come across this object, seems to be, we have this giant covariance matrix of size mn by mn. Even you write out the tensor product, this matrix is pretty big. And then if you have only one copy of the data, so we have only those sample collected from those people at a certain time, and we have only one sample for this matrix object, and then you want to do, convergence analysis for this large covariance matrix using one sample, this seems to be pretty unlikely. So at least that was my impression in 2010. And so let's look at the graph corresponding to A inverse and B inverse and its Chronicle product, which is called the Chronicle product of graphs. So I guess I will come to that object in a couple of slides. Before then, I will just show you what typically we say about graphical models. As I mentioned earlier, is we assume either have independent rows or independent columns, and then we want to estimate this sigma naught and its inverse using those ID sample. And the theta, which we typically call concentration of precision matrix, which is the inverse of covariance. For the Gaussian model, certain elements of the theta are assumed to be 0, and we want to use the sample, the ID sample, to obtain the set of zeros as well as the estimator for theta and sigma given the pattern of zeros. So this is a typical slide I show when I talk about the classical Gaussian graphical model. And in classical Gaussian graphical model, of course, the zeros encode conditional independence. So meaning if two genes are not connected, given the rest of the graph, that means these two genes are uncorrelated, independent given all the other genes. So here is a typical AR model for in time series, which shows every node just connect to two other nodes, and so depend on the recent past, you can forget about everything happened, in the previous examples. So clearly, the order of the sparsity is ON rather than ON squared in this example. And this is a star graph shown in a paper by Ravi Kumar et al. 2008. So he was a speaker yesterday. And the B is, in this covariance domain is a full matrix, but if you invert it, it is this hub-spoke model, which again is order ON. And of course, I threw in a lot of other independent random variables to make this graph look small. However, even within this subgraph, it is still sparse. So the Chronicle product of graphs is a very interesting object. So I believe there are many studies about this object recently in the computer science literature. But as early as 1961, there is this theorem which shows if you combine, this this hub graph with 6 nodes with a hub graph of 4 nodes, you get a very interesting object. So the left-hand side looks like a big wheel, and the right-hand side look like a starfish. So the coordinates, of course, just the coordinates from the vertices of G and then the vertices of H. So that would represent a coordinate on the product graph, and then an edge would appear in this product graph if the edges appear in the initial graphs. So for example, we can write this as G1, G2 originally belongs to E of G. And then if H1, H2 belongs to the E of H, then in the new graph, G1, H1 will be adjacent to G2 and H2. Of course, you can read this connectivity description from the adjacency matrix for corresponding to the Chronicle product of the 2 adjacency matrices for G and H respectively. And obviously, if you do this product for 3-dimensional graphs, so say ABC, one correspond to the latitude, and B correspond to the longitude, and C corresponding to 2 time points. And if you want to do a Chronicle product of these 3 domains, then you get a lot of edges as shown on the right-hand side. So I'll keep the left-hand side as a riddle, which I will tell you in a minute as I go through the talk. So here is another example of the complex data. So this is a map of the United States, and you can see from the grid is, those are the coordinates of the data points we collect from the wind speed data. And so this data set, we take the data set from 1948 to current, basically, in the last 70 years, and then we extract the wind speed data based on those 2 spatial grids. So this is we call Western, and this is Eastern. And so the Western grids, you can see around here, it is the Gulf, and in the middle is the Rocky Mountain, and then to the left is the Pacific Ocean. And in this highly reddish area, there are a lot of rugged mountains and the valleys and so on. So this is the graph we estimated using this data set. I'm not going to tell you which model yet, but you can see for the latitude factor, it looks like AR2, meaning each neighbor connects not only to its adjacent node, but also the next neighbor. And the longitude graph has a similar story. It also looks like an AR2, but in the middle it's broken, and this corresponds to the Rocky Mountain, because we know the wind is created by the pressure gradient of the air, and then the mountain acts as a barrier. So this shows the disconnectivity of these 2 components. And of course, those are the partial correlation graph, or the inverse, the precision graph from this data. And so this is the corresponding graph we generated from the eastern grid, and this is largely a AR1 model, except that there is an extra edge here. And the longitudinal coordinates also shows largely serial connectivity AR1, and then with occasion, AR2 substructures. So N2 is 50 years. So this is for both graphs, this is generated from 50 years of the historical data in January. So in January, we know there's no hurricane, there's no tornado. So the east, the east grid in the US looks pretty calm. And so here is the model we built. We actually used a Cartesian product to model the entire grid. So the Cartesian product is defined as follows. So if you think of this as a longitudinal, and this is the latitude, and you can give a coordinate, which is a longitude and latitude coordinate, and then similar to the product graph, each new coordinate in the Cartesian product has two coordinates, which can naturally corresponding to longitude and latitude. However, the graph is a lot sparser in that only the two nodes are only connected if they belong to the same latitude or if they belong to the same longitude. So for example, if I pick particular latitude, say this is 30 degrees north, and then I basically see a fiber which is identical to the longitudinal graph. And now if I pick a particular latitude or longitude, say 80 degree west, and I look at that fiber, which is just this path corresponding to the latitude graph we see in the previous picture. So the Cartesian product is a lot sparser than the Chronicle product graph. And this is very attractive in the sense that we can model some of the conditional dependency relationships in a parsimonious way. For example, let's go back to the study of twins. So suppose I want to study those features in childhood. So I want to keep so this is a very typical study in child development psychology. Is they have so many questions to ask about physical activities and task orientation or focusedness on some specific tasks, and other things like more characteristic or temperament like curiosity, openness, and of course you want to keep the child physically healthy, so you keep track of diet and BMI and so on. So suppose this is the hypothetical graph I want to build. I don't know what the edges look like. These edges I put in there are just based on some conjectures. And now suppose I have a twin sister, and the two of us participate in the study. So I can imagine the psychologists would want to ask the same questions about my sister and me, how correlated our diets are, which is obviously very correlated, and how correlated our physical activities are, which could be also very correlated before school age. And of course, they can also ask all these cross questions, say, how her activity or her BMI is related to my diet, or her physical activities is related to my, openness, and so on. But the point of using the Cartesian product is we just want to compare pairwise features rather than looking at all these cross edges. So this is just another way of building the model for conditional dependence. So the typical, so after I work on these models, I guess the common thoughts would be you want to analyze the projections. So the projections are defined as follows. So suppose I aggregate the data in these tensor or array or even higher dimensional objects. So that for simplicity, as I say, it's a 3D array. And so this is me, this is my twin sister, which does not exist. This is hypothetical. And so I want to study the, our childhood development across the, say, 4 to 20 years. So this is the direction I expose our data, and I treat all the other data as samples, right? So I will collect all my different features, and those are called the fibers. I will concatenate with all the fibers from my twin sister, and then I treat this object all together as a, as a single matrix, and I use the single matrix to study the development, between 4 to 20 years. What is the correlation? And similarly, so say those are the different features, right? So those can be our physical activity, IQ, and so on. So I expose the features, and now all my data across, 4 to 20 years, together with my sister's data from 4 to 20 years, are serving as sample, and we can use those collect sample to estimate the correlation between the features. And finally, if you want to do study about the twins, so this is me, and this is my sister, and I can do correlation study using the entire data from me and from her to look at the raw Pearson correlation coefficient, for example. And then you can imagine you have many other twin sisters or brothers, and then you can compute all these correlations across people as well. And so this is the initial motivation why I study the matrix varied data, is to say if you take 2 columns, you compute the Pearson correlation coefficient, and you call it gamma hat IJA. So this would corresponding to the raw sample statistic you want before you do inverse covariance estimation. And similarly, if I want to estimate B, I will take any 2 rows, and I compute a Pearson correlation matrix between the 2 rows. So in the gene expression data, this would corresponding to 2 of the people in the study, whether they are healthy or not. And the good news is, if you do statistical analysis, you realize even though we have a lot of parameters to estimate all simultaneously, they become easier to estimate as the dimensions and M grows. So the correlation coefficients, you can estimate them very accurately. In a sense, I will show you in formulas. And from now on, normality is not needed for the rest of the talk. Instead, you can just think about you want to estimate the inverse covariance matrix. And so that was based on a single data sample. Yes.
Yeah, in the previous slide, could you elaborate a bit more on like what's happening when N and M are growing, in the sense that the computational resources you need, that might also increase, right? So are you going to somehow like estimate them all together? So I was just wondering if you could elaborate a bit more on that.
Oh yeah, that's a very good question. So the correlation, the pairwise correlation computation is easy, right? Because that's just you do the inner product. So this is a raw statistical part, and then from the concentration of measure point of view, you get very sharp concentration, essentially identical to as if you have ID sample. Of course, this is under sub-Gaussianality assumption on the whole random ensemble. And I will show you the rate of convergence, in a couple of slides. And so essentially, the proof is based on Hansen-Wright inequality, which is quickly becoming a standard tool in our field. But when I was deriving those concentration bounds, I was using Gaussian chaos. And because I was dealing with matrix normal, so I have the tool of Gaussian chaos. And then a year later, I found the paper by my collaborator Mark Rudolphson and the colleague Roman Voshinen on Hansen-Wright for sub-Gaussian. So that basically makes the whole theory on matrix very normal to eligible for matrix very sub-Gaussian.
Excellent.
Yeah, I will talk about the computational complexity in a couple of slides. Thanks for the question. Okay, so that was based on single random matrix, and now suppose I have replicates. And it's the same story as I draw the picture earlier. I just concatenate many of the replicates and expose the feature I want to, estimate and construct sample covariance matrices using the outer products. So in this particular one, I'm constructing the sample covariance for those different features the psychologists may ask me and my twin sisters about. And then for S2, this is about our developing years. So say from age 2, 4, 7, 9, 10, 12, basically in our childhood, what is the developmental correlations across different years? And of course, you may think if you develop better earlier, it's a very good predictor for the later years, and we want to see that from the data. And so again, you expose, a direction such that you use the other direction as replicates. And so this goes to the very early estimator, which has a rate of convergence guarantee for this type of high dimensional complex data. So the estimator I derived, I call it the Gemini. So this is basically saying I take the sample correlation matrix, gamma hat A and gamma hat B. I use the graphical lasso to estimate the panelized covariance and the inverse. So if you are familiar, the graphical lasso returns you both the covariance and the inverse estimated simultaneously. So here I just write out as the sample. This is the panelized correlation matrix, and this is the panelized correlation matrix for B. And then you multiply a bunch of weights altogether to construct the final estimator, which you almost never need, because once you have the individual factors and you can just multiply by the weights, you can estimate a scaled version of A and B, and that's mostly what we need. And so as you asked earlier, what is the rate? So the rate for gamma hat A and for estimating the correlation coefficient ij of A is identical to the IID case, which is square root n downstairs, and upstairs is square root log m, say if m is larger than n. So I'm just taking the larger of these two. So I'm taking A as the large of these two covariance matrices. And this CB is some parameter related to the matrix, the spectral parameters of B. And the key thing to know is this can be killed if I do a three-step procedure. So the three-step procedure basically is the follows. So I estimate A and B using the two-step procedure. And after I get B, so after I get this initial estimate of B, I can use this B to decorrelate my rows to make the rows become independent, very much like what I did in the very beginning of the talk when I used the B to decorrelate the whole data, which contains the mean. So the idea is the same, is all the columns becomes isotropic, and I use those isotropic columns to estimate A. I get basically perfect rate of convergence. So you cannot beat this estimate, because even the constant is small. It's at most 16 if you kill C of B. So I would be pretty happy to use such a result and hand it over to people who does this type of analysis. And as a comparison for independent rows, if you indeed have independent sample, this rate is essentially the same as what is given above. So I will talk about the joint rate of A and B in the operator norm as a whole later in the talk. But for now, I want to continue the discussion about the Chronicles Sum model a bit and how to estimate it, because I sort of already gave you a story how to estimate the Chronicle product graph. And if you trust me, the rate is pretty nice. And the whole story is almost like, a fairy tale. And how about the Chronicles Sum? So the Chronicles Sum in an ICML paper 2016, Colette proposed the so-called bigraphical lasso estimator. So this estimator basically want to minimize the likelihood subject to the constraint that the precision matrix has this Chronicles Sum structure. So this Chronicles Sum structure is basically corresponding to the Cartesian product graph I draw earlier. And it also uses this projection idea is to say I compute the sample covariance matrices for the rows and for the columns, and I use those as sufficient statistics to put in my likelihood function. And so once S1 and S2 are computed, I do not need the sample anymore in this estimator. And instead, I solve this likelihood function, subject to the constraint that these are both positive definite components. So the penalty is put on individual precision matrices corresponding to the row and corresponding to the columns. So this precision matrix in the matrix form looks like this. So you have all these, diagonal matrices on the off-diagonal blocks. So these are basically identity matrices. So if you draw schematically, those are just sparse, identity matrices. And then in the middle blocks, you have those theta being added. So those are the structure. So this is the structure of a Chronicles Sum matrix. So this slide basically says, the big lasso objective is convex because the log that is a convex function and the Chronicles Sum is an affine operation, which I will revisit in a couple of slides. And therefore, any coordinate descent algorithm or any gradient, composite gradient descent type of algorithms would converge to the global minimum. So in the SCMR paper, we have a coordinate descent algorithm. And then 6 years later, with my former PhD student, Christian Greenwald, and the collaborator Al Hero, we published another journal paper, dealing with the same objective function, but now we allow the factors to be more than 2. So namely, we deal with a Chronicle Sum, a class of matrices, such like you can write out as follows. So for the sake of the talk, I will just use k equal to 3. So I will have I1, Chronicle I2, Chronicle psi 1. So I may have screw up the notation a little bit, but the idea is the same. So you basically have more block structures in this covariance matrix, in this precision matrix. And then similar as before, besides estimating those sample-wise and feature-wise covariances, raw covariance matrices, you can also estimate the covariance between the fibers. So in my analogy before, it will be this would compute the correlation between me and my sister with our entire history of data, as well as any correlation between me and other siblings in other twin pairs. So the Cartesian product has a very more nice property, as pointed out by the SML paper, is this associativity. So here is an illustration. So you may have seen Cartesian product more often than you realize. So for example, if I start with a graph of just a single edge, I do a Cartesian product with itself, I get Q2. So Q2 is just this square. And now if I do Q2 Cartesian product with a single edge again, I get a Q3, which is the 3-dimensional cube. And now I get, if I do the product of Q3 with the path again, I do not want to, make you feel bored. I get Q4. So basically, those n cube are just the nth power of K2 with respect to the Cartesian product. And why would this be useful? So for example, you can imagine this cube here, which is solid, can be used to describe the spatial, temporal, and time correlation for the wind speed. And then this, dotted hypercube cube can be used to describe the same, spatial, temporal correlation, but for precipitation. And we know the wind speed and the precipitation are correlated, so we can study them jointly. But also you can collapse them, right? So like what we did in the US wind speed study, we collapse all the historical data and use those time domain as replicates, and we just estimate a two-dimensional or two-mode product of a Cartesian product of the longitude and the latitude graphs. Okay, so I guess I talked so far about the Chronicle Sum precision models. So how many minutes do I have? I know we started a little bit late, but I didn't recall the starting time.
So maybe 5 to 7 minutes.
Okay, great, thank you. Okay, so let's go back to the matrix varied data. Without further ado, I just give you the theorem right away. So the theorem basically says I can estimate each of the coordinate of the gene almost perfectly. So this is the beta hat j minus beta j star, which corresponding to the mean for the gene j. The beta is a two-dimensional vector because one for the control group, one for the diseased person. And this rate is square root log m over n. And we know for high dimensional, from high dimensional statistics, this is the optimal rate you can get from the Gaussian extreme analysis. And then the operator norm for B is also depends on the sample size m, and also depends on the number of edges in the inverse covariance matrix. So, and there is another factor which is addition to the mean zero model. So in the Gemini mean zero model, we only have this term for the penalty. And now because of the mean estimation, we get this additional term. So this is a matrix L1 norm from covariance matrix B. And if this is large, so this can be at most square root n, our rate can degrade. However, that is the worst case estimate for L1 norm. Normally, we don't think we have such high matrix L1 norm for realistic applications. And so definitely this rate is enough for us to do the analysis for GLS. So this is sufficiently tight. And here are some simulation plots, so which shows the residual mean square error for estimating the beta indeed goes down for different topologies and for different configurations of the sample size and the dimension of A and B. So we treat, we look at A as an AR model and B as an Erdos-Rini random graph or a star block model, and so on. So the average Frobenius norm error also goes down as n and m increases, as I forecasted in the beginning of the talk. So here is the algorithm. So as I said in the beginning, we can just do sample mean. So that's the starting point. We take the sample average of the observed red vectors, and this is the sample average of the blue vectors from the control group. And we take those out from each individual according to its group. So this is a labeled sample. So we know which person has the disease, which person doesn't. And after, so in statistics, we call this centering. So this is center the data. Now, roughly it's mean zero. And we compute the gamma hat A and gamma hat B, as I showed earlier, using the Pearson correlation coefficient calculation. And I put in the Graph-Lasso estimators. And with the appropriate penalty, adding this additional term because of the mean estimation. And then I construct rescale to estimate B because I need this object to put in my GLS estimator. And absolutely, we do not care about the scale because you can see there is an inverse and there's an inverse and there's an inverse. So with all the inverse cancellation, the scale doesn't matter. If there is a scalar factor, it will all disappear. So we only need to estimate B up to a certain positive scale factor. And finally, to do inference, you need to calculate the test statistic. And upstairs is from what we estimated using the GLS. And downstairs is a plug-in estimate for the standard deviation for this gamma hat statistic for each coordinate. And so the second algorithm we do is to say, okay, if we estimated gamma hat using the GLS, if we believe that's a better estimate of the mean, why don't we do the following? So for certain genes, we know they are not differentially expressed. So if they are below the threshold, we just do global centering, means we just take the mean of all the sample out rather than based on the group. So on the top ranked gene, according to gamma hat, magnitude, we center the data based on the control or the disease group. And the reason we want to do this is because we believe, if you center those parts of the data, you can bring in arbitrary noise unnecessarily. So if so, we center the data slightly more carefully, and then redo the whole algorithm, we re-estimate B hat and so on. So indeed, this gives us very good estimate. And for the time concern, I'm not going to go to the simulations, but here is the outcome for this, Algorithmic collectors data. So as you can see, we estimated those inverse correlation based on the penalized method. And you can see all these blocks shows most of the twins still show correlation. And this is perhaps more visible when I show you the graphs. And then you can see some twin pairs are highly correlated and some are not. And some of the unrelated people seem to be correlated. So if I look at the penalty, and if I increase the penalty to 0.6, I think that's pretty high. And for the pairs who survive this high penalty, we can see those vertical lines are between the siblings. And then there are some actual edges between and among the diseased people. And more curiously, so if we look at this one, when we have the penalty 0.65, which is pretty high, we see those 3 people with the disease 1, 7, and 9, they are connected. So just before I give this talk, I look up the original paper in the page. So if our label is the same as their label in the paper, then it shows these 3 people are on some kind of steroid treatment. So this can cause unexpected sample correlation in the study, as warned by Ephraim. So we can also do this iteratively. Since we did it twice, we can do it 10 times. And every time we can rank the top 10 genes to see which are relevant. And this is more like just try to see how much noise can propagate throughout the algorithm. And so in the end, we see 3 genes, persisted among the top ranked 10 genes throughout this iteration. And we reported those 3 genes in our paper. So one of the genes is clearly related to gastric and colon cancer type of so in the literature, those are reported to be related to colon cancer diagnosis and so on. So that says our algorithm is able to uncover the signal despite the correlated noise. So I often was asked about the whole error for estimating the A Chronicle B as a whole, because in the previous theorem, I only care about B, so I only reported that. And so this is the theorem I proved back in 2014. So this is saying if you want to estimate the whole matrix Chronicle product, you get the sum of these 2 terms, one corresponding to estimate A, and one correspond to estimation error of B, and you sum them up, that is the error for estimating the whole Chronicle product. And so if you are familiar with the randomization theory, this is a saying in the classical Bayesian law, where we have those, a dimension of n over m or m over n inside the square root. Those are replaced by the corresponding sparsity, parameters. And these 2 summands corresponding to the convergence rates for estimate A and B, as I mentioned already. So in summary, the high dimensional setting requires us to consider the component of gamma as well as the inverse B among samples jointly, because if we have 2 samples, if we have 2 replicates of the study, let's definitely make the whole thing trivial, because from elementary statistics, the difference of 2 random variables from the same distribution has mean 0 and the variance doubled. And so you just need to do the subtraction of these 2 to estimate covariance, and then you do decorrelation. So that tells you why the single sample case is very challenging on the other hand. And so even with very simple two-group sample mean clustering centering scheme as a starting point, we improved estimation, essentially make it efficient from the classical theory on GLS. And so one can definitely replace the estimator with a node-wise regression, for example, and get even sharper rates of convergence. So in some of my ongoing work, I'm exploring this method for the mutual variate data also under missing values. So I will skip the whole theory on the Tensor Chronicles Sum because of the lack of time. So in conclusion, in this talk, I showed that complex data sets can exhibit partial correlations between both features and instances. And the associativity of the Chronicles Sum yields an approach for modeling data sets organized into 3 or higher order tensors. And we analyze this classical method, GLS, in the high dimensional setting where we need to jointly estimate the mean and the covariance, and normality is never needed thanks to the Hansen-Wright inequality. And we consider the sub-Gaussian ensembles and derive tight concentration measure bounds throughout the talk. So thank you very much. And here is a picture I liked because this shows our coordinates in space longitudinally. And so with that, I conclude my talk. I'm happy to answer any questions you may have.
Thanks so much, Professor Zhou. Questions?
Hi, Shuheng. Very nice talk. Very inspiring works. I have 2 questions. First of all, in order to achieve the statistical rate you have, may I ask the sample size requirement to say that how many samples, what's the N requirement to make the estimation possible?
Which one? Which model?
Yeah, all models.
Okay, so for the Chronicle product, you can estimate with a sample size N equal to 1 because you can make different type of assumptions. For example, you can say, A inverse sparsely is bounded by N and B inverse obviously. So the B is the smaller one. It can be easily bounded by M. So this is saying if you just make assumption on sparsity alone, you can assume you're estimating a subgraph, a graph, a matrix A with a lot of subcomponents which are disjoint. But you can replace the assumptions by some other assumptions. For example, as I cited here, in my original paper, I actually used a result from Kai et al. To so this paper, to make different type of assumptions on the covariance A and B to derive even tighter bounds. And then if you use a node-wise regression, your rate would depend on the maximum node degree rather than the total number of nodes. So that is sort of my ongoing work, but in the context of missing values. So that is for Chronicle product, you can start convergence with N equal to 1. And then the one I didn't get to talk to today about the Chronicle Sum is it's a lot harder to get the sample size N equal to 1. So this is the theorem I proved after our paper was published with Christian Greenwald and Alhero. But this is basically saying if you want to prove just a no replicate result for the Chronicle Sum model, essentially you need your data to be well organized in the sense that no dimension is going to dominate the rest of the dimensions, the product of the other dimensions. So for example, this one is an extreme, is saying if we have a very large dimension along D1, which is square root P, and then all the other dimensions, the product of all the other D2 and so on is also square root P. So then this component would be, this is something appear in the buy-in law, which is the nominal dimension versus the nominal sample size. This would become a constant. Then you will have a hard time converging to 0 for a single replicate. So unfortunately, I didn't get to talk about this today, but indeed you can make assumptions and make N equal to 1 work even for the Chronicle Sum model.
Thank you very much. Yeah, follow-up question for that. Yeah, I can understand if the matrix is of a square shape. So it means that to understand, to investigate the row-wise covariance, we actually have n samples instead of one sample, the number of columns of samples. Now imagine if the matrix is a very, for example, a very thin, say, shape. The number of columns is much more than the number of rows. And then to estimate the B matrix you have, you only have, say, limited number of samples, the number of rows, but you will have a very, very high dimensional objects. In that case, will your result be different? Can we still estimate A and B if we only have one sample?
You mean
just
for Chronicle product or sum?
Yeah, Chronicle product.
Okay, so for Chronicle product, if one dimension is really low, and it depends on if you want to estimate the diagonal or not, right? Because if you need to estimate the diagonal of the other dimension, I guess it depends on whether you want to estimate the factor or not.
Okay.
So, so this result basically shows you need the n to be at least as large, of the log, right? The log term. So n needs to be at least the square root log of m, and also you need to dominate the number of edges in the other graph. So I guess if B is really, so if A is really simple, then we just go back to the classical result, right? So if A is really simple, close to an identity matrix, then whatever sample constraints we have in the ID case would apply to that case. At least that would be my intuition.
Now I can see from your bound, you need n to be greater than equal to sparsity times a log term. So I think that's the
right. So this log term
yeah.
is unavoidable. At least I didn't work to make it go away, because I thought at least this is very typical in high dimensional statistics. Okay,
I understand. One more, just a quick question. So you proposed several models to model this let's say matrix random sample. Which one should we choose in practice? Can you give us some guideline?
Well, that's a very good question. So actually, when I talk about this US grid, I would want people to put in the vote in the chat. Do you think the geographical, the spatial correlation matrix or partial correlation matrix, do you think it should be a product or a sum? So I know there are, people are probably not able to do chat right now, but I think it really depends on the contact we have. So for me, it looks like in this geographical setting, Chronicle Sum is pretty attractive because, first of all, it's a non-separable model. And I know in spatial temporal domain, people have a lot of agony against the Chronicle product. But Chronicle product, as you can see from the theory, it is slightly easier to estimate. Probably precisely because of its separability, representation. So I feel if you don't know your data type, if you just want to try something out, Chronicle product is a pretty good starting point. And then you can refine your estimate to say what would happen if I try the Chronicle sum as well. And obviously, the sum is more or less like a subgraph of the Chronicle product. So it's almost like if you have a dense graph, how do you trim it off so that you get a parsimonious model to explain your data? So it's almost like in that sense, I think Chronicle sum is more sophisticated a model.
Thank you. That makes sense.
So I know I'm on recording, so I'm a bit hesitant to make such predictions, but indeed, I feel the Chronicle sum is probably going to be very useful in the spatial temporal domain. But the Chronicle product, as always, is like a a very old friend of mine. And I always like to try it out on the real data to see how that tells me about the story of the sample correlations.
Thanks so much, Professor Zhou. So in the interest of time, I'm probably going to close the questioning session and we're going to resume at 3:25. Let's thank Professor Zhou again.